I'm a hydrogeologist. My motto in life is think out of the box. My name, Marcel. My experience, groundwater and soil contaminations. I'm the creator of Geo RGB, a channel of geographic information systems, GIS, geology, hydrogeology, and contamination. The purpose, the objective, the goal, the intention, the target, the desire. Share my experience and acknowledge to create points of discussion. The Geo RGB community. Promote the use of free and open source software. A free digital society. Provide technical advice to environmental companies. An opportunity for professional growth.
All rain on Burnaby. At 12:31 p.m. on July 24, 2007, an excavator accidentally ruptured a crude oil pipeline in Burnaby, British Columbia, Canada. The oil spread the area for approximately 25 minutes before the flow was stopped. Approximately 250,000 liters of crude oil was spilled. About 7,000 liters of oil entered the storm drain system and eventually reached the waters of Warren Inland. Hello guys and welcome back to my channel. This is the second and last part of the videos related to ASTER satellite imagery oil spectral signatures. The topic for today is related with the analysis of spectral signatures using the software Snap and also the Quantum GIS with the plugin SCP. The Snap software is a free software from the European Spatial Agency and it's known as a Sentinel application platform. This software was developed to use with the Sentinel satellite imageries, but it also supports numerous sensors other than Sentinel. Let's go to do it! At the previous video we was talking about some of the characteristics of the sensor ASTER. Also we saw how to download the satellite images from the USGS Earth Explorer website. And at the end we was processing the satellite images using the SCP plugin on Quantum GIS. Remember that if you missed that video, you can hit the card located at the top right corner of your screen. To start, let's go to load the satellite imagery that we processed the other day. It was a raster image. Then here it is inside this folder and it is reflectance. Remember that we processed the image to convert the digital number in reflectance. And as you can see here, we have 14 different bands. Then let's go to select all these ones and open. And add, close, and the first thing I would like to do is take all these ones out, is to analyze the pixel resolution. Then I'm going to create a temporary band set. To do that one, just go here, press this option here to refresh. Then all the bands is going to be loaded over here. Then select from the first one to the last one with a shift on your keyboard. Then press the last one. Press this button here to add all the bands to the band set. And then here select the sensor you are going to use. In our case is ASTER, from bands 1 to band 14. And as you can see here, now we have the center weight LAN. Then after that one, you can go to this option here and select a band composition. I'm going to select this one, for example, and wait until the temporary layer is loaded. It's this one. And now I am going to load some vectorial layers I created with the dimension of the pixels. Then this one, you have to go back here, shapefile, and it's this layers over here. I'm going to just load the shapefiles. This one, I press Ctrl to select the next one for the 30 meters. This one, and also the last one is going to be the 90 meters. And open, and add, and close. And now I'm going to make zoom to go to this vector layer. I created these different layers with layer, create layer, and new shapefile layer. Then select here the name of the layer. In this case I put these names. Then what I did is select the polygon and then the reference coordinate systems. It was this one. And then OK, and you are ready to edit the layer. Then I press the pencil to edit the layer. I selected this option over here and I selected the third option. Then what I did is just copy the pixels from the different bands. Then I'm going to show you here. I'm going to take all these ones out, and let's go to start, for example, with band number 1. As we know already, let me show you here. Here we have all these packages. We can make the difference between these packages because of the pixel resolution. In this case, we have from 1 band to 1.3, it's 15 meters, from 1.4 to band 9, it's 30 meters, and from band 10 to band 14, it's 90 meters. Then we can take any of these bands to copy the pixel resolution. Then to create the shapefile for the 15 meters, I selected the band 1. And as you can see, and what I did is just copy 4 pixels from here. Right, as you can see, it's the same one. Then for the 30 meters, what I selected is the band 4. I'm going to take this one out, band 4, and I copy also the pixels over here. As you can see, for 30 meters, I copy all these pixels. Then what we have here is 30 meters for these pixels and also 15 meters for these pixels over here. For the last one, what I did is select a band, for example, band 14, that we know the pixel resolution is 90 by 90, and I copy again the pixel, just 1 pixel. And then at the end, what we have is all pixel resolutions. From 90, that's the biggest, to 30 to 15 meters. With the visualization of the pixel resolution, we are going to have a better understanding on the relation between of the pixel resolution and the scale of the event, in this case the spill of oil. In order to see this relation, let's go to load also the panchromatic satellite imagery. Then it's a raster, this option here, go here, and is this image. If you don't know how to get Google satellite imagery of high resolution, I'm going to leave a card on the top right corner of your screen where you have a video tutorial. Then open and add, and then close, and I'm going to put this one over here. Now I am going to make all these layers transparent to see better. Then here, this one transparent, apply. Even I can change the color for a red one, for example. Okay, also I'm going to make this one transparent. And now I am going to take all these ones out. And as you can see, for a 90 meters, the pixel covers all this area. Then if I take this one out and I put this one here, you are going to see that the band set composition is this layer over here. For a 90 meters, it covers all these pixels, that is 15 by 15. It means, for example, that if we want to calculate the band 10, the value for the reflectance with band 10, all these pixels are going to have the same value for the reflectance for band 10, because the resolution of the pixel is 90 by 90 and it's covered all this area. However, when we are doing the band composition, the pixel show at the image is with the maximum resolution, in this case 15 by 15. But you have to be aware that when we are taking the measurements of all these bands from band 10 to band 14, for all these pixels we are going to have the same value. For example, for band 10, if we measure the reflectance in this pixel, is going to be, for example, 2. But if we measure over here, it's going to be also 2. The same is going to happen when we are taking the measurement of from band 4 to band 9, where the pixel resolution is 30 meters. Then in this case, for example, if we are taking the measurement of the band 4 for the reflectance, all these 4 pixels are going to have the same value. And if we are taking the measurement for band 5, for example, in these 4 pixels, they are also to have the same value, because the resolution for bands from band 9, from band 4 to band 9, the pixel resolution is 30 by 30. Then the last one, the pixel resolution for 15 by 15 is from band 1 to band 3. And in this case, we can measure individually every pixel. Now we can compare the pixel resolution with the scale of the event. Then let's go to put this image here on the top, and let's go to bring this picture over here. That's the spill. And as you can see, let me make some zoom over here. A little bit less, and I'm going to take this one out, bring the image again. As you can see, this house over here is this one here, this house is this one here, and these trees over here are these ones over here, and this big one here is this one over here. And then the spill area, it's approximately over here, and all this area over here. Right? Then when we add the pixel resolution of 90 meters, as you can see, the area it's covering, it's really big, but the oil is just in this area. But we have to understand that the value of the reflectance is going to be the average of all this area. But if we have oil just in this area, that it represents maybe, I don't know, maybe 25% of all this area, it's not going to be representative of the oil, right? The value of the reflectance. Because of that, I decided to not use the bands related with 90 by 90 meters, because the scale of the event compared with the pixel resolution, it's quite small. For the 30 by 30, this one, let me put the image here. As you can see, that one could be used because, you know, the area of the pixel, it covers this area, right? And in this area we have the oil, and the value for the reflectance is going to be pretty significant, and the same is going to happen by 15 by 15, right? It is covering a very small area, and that's also pretty good to identify the spectral signature of the oil. The next step is to identify if we can see anything anomalous or weird on the band composition, to see if we can identify the spill. Then take this one out, put this one, take this one out, and if we make a zoom out, we can see that in this area there is something weird on the band composition. Even we can change the band composition to have a better view of the spill. You can play with the bands and select whatever you want and decide what is the best. Just try different compositions and check what is the best. As we are adding, for example, these bands, the pixel resolution is worse. The best resolution is from bands 1 to 3. Here, for example, in this one, you can see something really weird over this area. We have to understand that the road is this pink colors, and here the pink color is break, right? And it happens on the picture. As you can see, we have here the main road, and the main road is covered by the oil. And we can see something weird here at the image, on the road. If you, for example, put here bands from, I don't know, 10, 12, and 14, now the pixel resolution is so bad, right? Then maybe the best combination is just make a mix of bands with 15 meters pixel resolution and, for example, one with 30 meters resolution. If your intention is to work with, for example, all these bands from band 1 to band 9. But if you want to have the best resolution with the pixels, you have to work just with the 3 first bands from band 1 to band 3. And I believe that one, the one we tried before, 132, it's a good one. Other important thing that we have to consider is that this satellite image, it's not the same as this panchromatic image. This one, if we check with Google Earth, this image is the same as this one here, the same as this one, and this one it's from 2019. But as we know, the satellite image here is from 2007. Then we have to be very careful with that kind of things, just to make sure that we are comparing the things in the same situation, in order to see if there was something weird on the landscape. Because as you can see, for example, these big trees over here, they make some dark pixels, and that's something important to consider. And what we want to see if there is any change on the landscape in this area during that years. Then to do that one, we can use this tool from Google Earth Pro that can allow us to identify different years on the panchromatic image. Then go here, select this option, and we can go to 2003 and see if the landscape changed. I mean, for example, we have trees over here that can make the satellite imagery in 2007 dark also over here. But as you can see, now we are in 2004. Also this one, 2004. The landscape, this one is from 2007. But unfortunately, it is covered with snow. But in 2008, here you can see they replaced the pavement in this area because of the spill. But there is no change on the vegetation, right? Here we have 2004 and we have these trees over here and this small here, but there is no big trees over here as we have in this area. The picture from 2004, I believe, is better to see that one. Here we have big trees and also here, but not in this area. (2012). And also what we are going to do now is compare different satellite imageries from ASTER from different years, also to compare the pixels with respect to the event on 2007. Then let's go to close this one. Also, we can use the pictures from the news to recognize the landscape. In this image, we can see the trees and what is the size. In this image also, in this one, in this one, and etc. Other thing that we have to consider is that this satellite image is 1 day after the spill. I understand when the spill happened, they try to contain the oil, and I don't know what kind of things they did. As you can see, for example, in these pictures, there are some gravel or sand or clay that they may be used to contain the spill and also to absorb the oil, maybe. Because, for example, sepulite, it's a kind of clay that can be used as an absorbent for hydrocarbons. And I don't know how they contain the spill at the beginning. And then the satellite imagery we have, for example, in this area, maybe the spectral signature, it's not 100% from oil. Maybe it's a mix of something, you know, maybe sand or clay with oil, and that's what it is, right? But we can use the methodology I'm explaining here in this video to analyze any kind of event with satellite imagery. One of the inconvenients I found using this satellite imagery from ASTER and the panchromatic image from Google Satellite is that both images doesn't match well. As you can see, for example, if we take this road as a reference with this circle at the middle, when we see that one on the satellite imagery, let me take out a little bit of zoom. And maybe this one is not the best. Let's go to change for 1, 2, 3. 2, 3, 3, 2, 1. This one is better. If we take that road and this circle as a reference, what we can see is that the image doesn't match really well. You see, we have the road here, but the satellite image looks like the road it's over here. It's not at the center over here, it's a little bit over here. You see? And that is a big problem when we are working with very high resolution, because we don't have too many pixels with oil on the spill area over here. Remember when we put the pixels for 15 meters? We are looking for to take the pixels over here. And if there is discrepancy between both images, we are not going to take the pixels properly. And that's the reason because I decided to work also with Snap software. I'm going to show you now how to download this software and how to use it. Just to download the software, Snap Sentinel, and just the first option. Click over here. There are different options. The one I'm using is this one for 64 bits for Windows. Then just press this button, download, and run the software. This is the software, and unfortunately I have to say that this software it's not fully developed to use with ASTER images, but we can use some files. It's not going to be the same files I'm using for QuantumGIS. It's a different one, but we can make some things. I'm going to show you here with this one. I put already here some data. I select the world features. I put Burnaby. Then I'm going to select this one. And I put also already the range of date from July 1st, 2007 to July 30th, 2007. And then here I'm going to select the sensor, ASTER is the first option. Okay, and here I'm not going to add any special criteria, and then I'm going to press results. I explained at the previous video how to do all this stuff, then that's the reason because now I'm past very fast. And here are the download options. The other day we downloaded the standard product, but to use with a Snap we have to download the visible product, and that's what I did. I'm going to show you now. This is the 2007. This one is the file we downloaded the other day, the standard product, and this one here is the GeoTIFF file. That's the one we are going to use with Snap software. And I also downloaded different files from different dates that I am going to talk about these files a little bit later. Then I go here and I'm going to load that data. Then what I want to do here is file, import, generic formats, and I'm going to use the GeoTIFF. Then I go to satellite image and I'm going to load the image from 2007. As you can see here, in July 25, 2007, that's the one I want. I have also image from 2016. I have also image from 2006, August 25, from September 15, 2008, from September 21, 2005, and also for July 25, 2004. But at the moment I'm going to load this one. Also I am going to load the image from 2006. GeoTIFF 2006, this one, import, and also the panchromatic image from Google Satellite. Generic format, GeoTIFF. Go back, is this one, import. Now in order to create the image, what we have to do, we have for this image just 3 bands. Then go here, click right on your mouse, open RGB image windows, and here we are going to select the composition 231. 3, 1. Okay. And now I am going to do the same, but for this image. 2, 3, 1. 3, 1. Okay. And I am going to open this one, but with this one I'm going to leave the real color. Okay. Then I am going to press this option to see the 3 images. I have this tab for the first image. This one is from 2007 for the year of spill. This one is from 2006, August 25. And this one is the panchromatic. Then I'm going to press this option here to see the 3 images, or also you can go here and put this one tile vertically, or windows horizontally. And as you can see, these 3 images are synchronized. But to do that one, you have to press this option here and also this option here to synchronize the pixel. Then let's go to move to our location is over here. That's the area where the spill happened. And as you can see, the area with dark pixels is this area with the vegetation. As we move on the panchromatic image, you can see how the pixels change over here, right? Then where we are here, we have these dark pixels and also these dark pixels over here, corresponding to these trees over here. But this one is from 2006 and this one is from 2007, and here, as you can see in this image, we don't have any dark pixels over here, but we have in over here, but nothing over here, and that's corresponding to this area. As you can see the pixels, how they are moving, and then that's the pixels that we want to analyze. These 2 pixels over here, this one and this one, they correspond to this area over here. Then we are going to take these 2 pixels to characterize the spectral signature for the oil, and also we are going to take these 2 pixels over here as a background, and also these 2 pixels over here, because they have similar characteristics, right? And I believe these 4 pixels are going to be a good background to compare the values over here. And we are going to compare all the pixel values for 4 different years. We are going to do that one for 2004, for 2005, for 2006, and also for 2007. If you want to see just one image, then click this option here, go here to just see one of them, and okay. And then we can have a general view of the area. This one is for 2007, where we identify something weird over here. This is from 2006, where we cannot see anything weird over here. And then we decided the pixels over here has something interesting to analyze. Now let's go to Quantum GIS and load these pixels on the software. I have already the layer created. Then select vector here, go here, shapefile, and it's going to be the pixels. Then open, add, and close. And I am going to edit these ones a little bit to see better. Properties, symbology, I want this one transparent, and I'm going to make this one with a yellow color because I like it. That one is going to be 0.5 and it's going to be a dash line. Apply and OK. And that's the pixels we are going to analyze. This one for the potential oil spill, and this one as a background. Then if we take the panchromatic image, we can see here the pixels. The next step is to create the proper virtual band set, where we are going to use just the bands from 1 to 9. As I said previously, we are not going to use the bands from 10 to 14 because they have a 90 by 90 pixel resolution. Then to do that one, what I am going to do is take this one out, remove. Okay, and I'm going to take also from 14 this one, remove. Then I am going to open the SCP band set. I'm going to refresh this one to load all these bands over here. Then I'm going to remove this one, yes, and load the new band set from here to here, add, and I'm going to check that it's correct. 1 2 3 4 5 6 7 8 9. Then remember to select this option here, but that one is not changing this one, and I don't know why they doesn't change. Okay, that now is good, and now we are ready to create the new band set. The center of the wavelength is these values over here. Then if we plus this value, that's the minimum and that's the maximum, and then divided by 2, we are going to have this value over here. That's the center, and that's the same for all the wavelength. Then just go here to the band composition, and that's the new virtual band set. Now, in order to create the spectral signature, we want to open the SCP doc panel. Just check here, that's okay. And also a really important thing before to do the spectral signature is make sure that you have this plugin, the SCP totally update. Then select the plugin and press this button here to upgrade the plugin. I did already because sometimes it doesn't work properly. You have to do that one. Now to do the spectral signature, we are going to create a training. Then press this button here. I'm going to rewrite this one that I did already for 2007. Then save. Yes, I want to replace. And I'm going to remove all these ones. Yes. And yes. Okay, now I don't have any of these ones. Then select this option here, put here number 1, and also here number 1 because we are going to work just with 1 pixel. Select this option and click on the pixel you want to analyze. First, let's go to add number 1 here to start with the number 1. And now press this one to select the pixel, and then press this one to save the spectral signature. And I'm going to do the same for the rest of the pixels. Now here at the dock panel we have all the spectral signatures for all the pixels from 1 to 6. In order to see what is each pixel, you can edit this layer over here, the training one, then go to properties, go here to symbology, make this one transparent, go to labels, select single label, then select the parameter you want to see. Is going to be this one, then make a buffer, and for the location is going to be the first option, apply, and OK. As you can see, this one is 1 2 3 4 5 6, this 1 2 3 4 5 6. Then we have to select all these ones and press this button to see the spectral signature. At the x-axis we have the waveland. At the y-axis we have the values for the reflectance, and each dashed line is the bands. Then this one is the band 1, and the values for the band 1 are these ones over here. Even it says minimum and maximum, we have the same value. And we have for each pixel, we have the bands from band 1 to band 9. From band 1 to band 9. Then what I'm going to do now is change the colors of the bands. Just select this option over here, and this one is going to be brown. And I am going to move the legend over here. And I'm going to export the image with this option. And okay, close. And that's what I did for each of the satellite imageries from 2004, 2005. This one is 2004, this one is from 2005, this one is from 2006, and for the date of the spill, one day after the spill, from 2007. And what we are going to do now is analyze all the spectral signatures for the pixels and also for the different years. What we have to understand from this graph is these values over here for each pixel. For example, this one from band 1, this one from band 2, this one for band 3. They come from the satellite imagery for each band. I'm going to show you. For example, let me close this one. If we go here and take the virtual band set out, and let's go to open, for example, band 1. If I press this option over here for information and I click on the pixel, I'm going to get the value of the reflectance in that pixel. For example, this is the value for pixel number 4 for this one here. The number 4 is the one, the green one, then this value over here. And we can check any value for any of these pixels and also for any of the bands. For example, if we go to band 9 and we press over here, we're going to get the pixel value. Now I'm going to show you all the graphs I created from 2004 to 2007. I didn't did anyone from 2008 because, as you know, in 2008 the shortwave infrared stopped to work and we don't have that bands on the sensor ASTER. Then let's go to see how they looks like. That one is from July 25, 2004. This one is from September 21, 2005. This one is for August 25, 2006. And this one is from July 25, 2007. And this one is the one for the spill, one day after the spill, I mean. Now I'm going to show you an image where all the spectral signatures for all the years are compiled. The first thing it called my attention is that for the years 2006, 2005 and 2004, all the pixels show approximately the same pattern. As you can see, for August 25, 2006, all the pixels has this pattern. In 2005, they have this pattern. And in 2004, they have this pattern. But what happened in 2007, the year of the spill, we can recognize two different patterns. One is this one, and the other one is this one. Right, with this thing over here. And that's pretty interesting, and it's indicative of something. As we can see here at the graph, the brown and purple line are corresponding to the pixels 1 and 2. Is these pixels over here? Let me put this one, not the virtual one, this one. 1, 2 is the area of the spill. Maybe this one is better. Is the area of a spill, and is the brown and pink. The 3 and 4 is the blue and green. This one's over here, and they correspond to these pixels. That is the background, and 5, 6 is also the background. And here at the graph, it's with color lilac and black. And we have the same legend for all the years. Then other interesting thing that I can see in this graph, it's the values for the reflectance. As you can see, for band 1 in 2007, the pixels 1 and 2, they have a low reflectance with respect to the other ones over here. However, it doesn't happen all the other years. As you can see, in pixel 1 and 2, here we have the highest values for band 1 in 2006. In 2005, they are pretty close each other, but also here we have the highest values for band 2 in this case, and for band 1 we cannot see. And in 2004 we have again also the highest values. But in 2007 there is quite difference, and the values are the lowest one. The same happened with band 2. As you can see here, we have the lowest values for pixel 1 and pixel 2, but here that pixels are at the top in 2005, and also here we have this one and this one. They are also at the top in 2004, and in 2006 they are again at the top. But it doesn't happen in 2007. And also the same for band 3. As we can see, we have the lowest values, and there is big difference. Here in 2006 we have the pixel 2 here at the top, and the pixel 1 is over here. They are almost at the top. Here it's pretty clear they are at the top, and here also they are at the top. But in 2007 they are at the bottom. My interpretation is that, as we know, these pixels are the potential with oil. It means that the oil absorbs the energy, and that's the reason because we have low reflectance. Because as we can see at the previous year, where we don't have any oil, these pixels are the ones with the highest reflectance. With respect to these bands over here with the shortwave infrared, because we was talking about these bands over here, the visible spectrum electromagnetic and also the near infrared, but for the intermediate wavelength, the behavior, there is not too much difference. I'm going to say that for all the years we have more or less the same behavior. Here for pixel 1 and 2 we have the highest values for band 4, but also we have the highest values over here. Well, it's not the highest because pixel 5 has the highest value, but they are very close. In 2005, again we have the highest values, and in 2004 we have the highest values, and that's the same what happened in 2007. And for the rest of the bands over here, they have also pretty similar behavior for all the years. Then what I'm going to say, that for the shortwave infrared, the oil doesn't have a influence on the spectral signature. The biggest influence is on the visible part of the spectral electromagnetic and also the near infrared. To finalize, I would like to mention that I created this project with 3 sources and also 3 software. I didn't pay anything for the satellite imagery and anything for the software I use, and that's the result I get. It is obvious that I found some limitations when working on the project related with for example, spatial resolution. The spatial resolution, it's the same as the pixel resolution. As we know, we have a resolution of 15 meters and 30 meters, and for the scale of the event, maybe this pixel resolution it's too big. Maybe it's going to be better small pixel values for the reflectance, where we be more accurate for the location of the oil. As we know, when we are taking the value for the pixel, it's an average of all the area, right? And as you can see here, we have a tree, we have pavement, sometimes we have I don't know, over here the same, and maybe we have a piece of house and a piece of garden, and you know, the pixel resolution in this case, I believe it's quite big, and that's one of the limitations. Other limitation is related with the number of bands. As we know, we was working with 9 bands, but for the shortwave infrared there was no influence on the oil, right? And then what we was doing is just work with 3 bands, and this is very poor to identify the spectral signature, right? As more bands we have, the spectral signature is going to be better characterized, right? But in our case, we can say that we was working just around with 3 bands where we found some differences. And the last limitation, it's related with the temporal resolution. In this case, for example, for July 2007, I have just one satellite imagery for this sensor, and that's very poor. Even when I try to get some satellite imageries from July from previous years, it was sometimes even hard, because maybe the satellite imagery for that day, it was with a lot of clouds and I couldn't use it, and maybe it was just from July. For example, in this case, the closest one to July 25, it was August 25, and in this case in 2005 it was for September 21. Then for ASTER satellite imagery, we have sometimes just one satellite image per month, and even sometimes that image is not good because there is clouds and you cannot use it, and that it's also a big problem. Because what I would like to have is, for example, several satellite imageries for July, right? Then in that case I can compare in a more realistic way, because the temperature and the conditions are going to be pretty similar, right? But if we are changing from July 25 to September, the temperature is different, the energy of the sun is different, and we can find too much differences on the spectral signature. And then that's another limitation related with the temporal resolution of the satellite imagery. In this scenario, the ideal device to characterize the spectral signature, I'm going to say it's a drone, where you can have a multi-spectral sensor where you can capture a lot of different bands from the visible and also near infrared spectrum electromagnetic, with a very high pixel resolution, about 1 meter or 1.5 meters, and also with several images, not just from the day of the spill, that it's also really important, but also after the spill. And I can say that before the spill you are not going to have anyone, because you are not going to fly the drone before the spill happened, right? But you can have access to private satellite imagery where the temporal resolution it's better, where the spatial resolution is better, because you have a small pixel resolution, and also where the spectral resolution can be a little bit also better. Okay guys, thank you very much for watching this video, and see you on the next one.